In the third example, we have a hexadecimal expansion of a hexadecimal number, which is another way to say it is that we can convert this hexadecimal number into a decimal number by following this process. Okay, so in the hexadecimal expansion, we have equivalents of digits ranging from 0 to 15, 0 to b minus 1. So we see that here we need to express these digits by using letters from A to F. Okay? So A represents 10, B represents 11, and so on up to 15, which is represented as F. All right, so this is a hexadecimal number, which means it is represented in base 16, and it has 4 digits. Okay, so again, I must mention that digit is something is a name that we refer to the decimal representation, but we are using this just because we mostly deal with the decimal numbers. So in this case, the least significant digit of this hexadecimal number is F, which is 15, and similarly the most significant digit is 3. So we see how we can expand this by using different weights. For example, F or 15 has a weight of 16 raised to power 0 because 16 is the base in which this number is represented. Then we have a 0, so we can skip this 16 raised to power 1 term, and this is followed by a term which is equivalent to 10 because a equals 10 in hexadecimal representation. Then we have a weight of 16 raised to the power 2 for this digit, and 16 raised to power 3 for the most significant digit. Okay, so when we add all these numbers, we get the decimal representation of this number, and you can see that the decimal representation is actually has more digits than the hexadecimal. Okay, because hexadecimal is a more compact representation, is a bigger base than base 10. I hope that this clarifies the expansion of integers into an arbitrary base.